This is chapter 18, another chapter of thermodynamics. It is one step further from what we learned in chapter 5 in Chem 1 class. Before we start off this chapter, I'd like to review a little bit from what we learned so far since Chem 1 class. When we deal with the chemistry, especially when we study the chemical reactions, there are always three questions that we want to ask and answer. First, what happened? Second, how fast the reaction takes place, or how fast we can get this reaction done. The third, am I wound up with a good yield, or to what extent does this reaction take place? We spent pretty much an entire Chem 1 course talking about what happens. We start with atoms, with the atomic theory, electron configuration. Then we study the compounds, ionic compound, covalent compounds. We talk about the Vesper theory, try to understand the structure of a certain group of compounds, which is covalent compounds or the polyatomic ions, so on and so forth. By doing so, we just hope that we can understand the chemical properties and behavior of compounds or the elements by studying their structures first. Once we realize that we understand, or better yet, we predict the behavior and the property of the substances, we can start off the reaction. So we learned quite a few types of reactions. And of course, the most important type of reaction in our chapter is pretty much acid-base reaction, as you have seen that already. And of course, the grammar check of this all chemistry, if you consider chemistry as a language, is a stoichiometry. So we spend a lot of time learning how to do the calculation. So that is for Chem 1 class. So we focus on what happened. Starting in this Chem 2 class, in chapter 14, we put our foot into some river, try to handling the temperature, like kinetics. So we want to know how fast the reaction can go. We discussed the two rate laws, and even though we understand that each law has its pros and cons, and the both can do the job depending on what the reaction that we can study. From the rate law, we realize it is the rate constant that plays a much important role in order to determine how fast or how slow the reaction can go. And then we related the rate constant not only with the temperature here. As we said, the rate constant is a function of temperature. We also related the K, the rate constant, with a term of energy we call activation energy, as shown up right here. Now we understand for any chemical reaction that takes place, there must an energy barrier for reaction to overcome or pass through. Depending on how high the activation energy is, the reaction becomes slow or fast. Of course, the smaller the A, the faster the reaction can go. And of course, with that in mind, we apply this knowledge in action so we can have catalysts. So we try to apply the catalyst so that we can change the pathway of the reaction by increasing or decreasing the activation energy to make the reaction takes place at the rate we expect. Of course, in medicine, we want the reaction to slow down, okay, so that we can increase the activation energy by setting up the pathway or by putting a particular drug. As a matter of fact, the drug inside our body, in the view of chemistry, is a catalyst. And of course, in chemistry, we want to develop the catalyst that can lower down the activation energy so that the reaction can take place much faster if the reaction is slow. But I just want to remind you, at the end of this chapter 14, we said no matter how great the effort we put on the catalyst cannot change the ratio of product and the reactant. And of course, we leave that to the delta E. And the delta E actually is the heat of the reaction. We said the ratio of the product and reactant actually is determined by the delta E. In chapter 15 through chapter 16, we have learned a lot about thermodynamics, especially the thermodynamics we apply to the chemical reactions. So we introduce one of the greatest concepts called equilibrium constant. Okay, and of course we learn a whole lot of K's, of KE. So KC, KP, KA, KB, KW, KSP, so on and so forth. And those K, whatever we want to call it, but in this chapter, we just combine all of them, we call it KEQ, equilibrium constant. It is the KEQ determines the extent of the reaction. In other words, it determines how much of a product that we expect from the reaction. So it is a KEQ tells us the degree of the completion of the reaction. Now, remember the delta E that we have discussed in chapter 14. Here in chapter 18, after we have learned all that equilibrium stuff, we want to have a better study or deeper understanding about how this delta E can relate it to our equilibrium constant. Is that going to be a very obvious relation that we can foresee, or we need to do a little bit of something more so that we can have this related? But before we talk about the whole thing here, so the KEQ related with some energy term like a heat of a reaction, so on, we must understand what a spontaneous process is. Because this is thermodynamics, there are a few concepts that we learned from chapter 5. I want you guys to go over. First, system. And we understand a system is something that we want to study and we are interested to study. And for system, it must have an internal energy. And every pure substance must have its unique internal energy. That means, for example, carbon dioxide, since it's pure, it must have its own internal energy, which is we call standard heat of formation, delta H0F of carbon dioxide. Another concept is called surroundings. Surroundings are everything else outside the system that can exchange energy and or substance with the system. And we already know that we need to put a little bit of limitation on the surroundings, because if we don't, everything else, including you and me, could become a surroundings of something that we study. So the limit on the surroundings would be anything that is directly relevant to the system or anything that has directly interaction with the system. So that cut down a whole lot of surroundings that we thought could have something to do with the reaction or the system. So that put surroundings very limited, and it's much easier for us to study. As the example we shown in this picture. And this is the system, the reaction going, and everything else inside the picture becomes a surrounding. You and me are no longer surroundings, and we can just be bystanders. We are outside of this universe, And speaking of universe, okay, universe is the system plus the surroundings. Of course, just like a system, surroundings and universe must have their own energy as well. All right, now let's talk about a spontaneous process after we jog our memory a little bit about some terminologies that we learned from chapter 5. Spontaneous process is the process that proceeds on its own without any external influence. For example, like a waterfall. Waterfall occurs automatically by its own. So waterfall is what we call as spontaneous process. Just like this occurs by itself without external and continuous input of energy. Waterfalls exist no matter what we want to do about it. So sometimes we don't have to do a thing, right? It happens on its own. But in chemistry, however, we may need a little bit of initiation to have the reaction to take place. So for example, we need a little bit of sparkle in order to have gasoline react with oxygen. Once the reaction starts, the reaction will go out by its own. So that's a little bit of initiation input of energy is okay for a spontaneous process, because that a little bit of initiation of energy is what EA is required for a very small portion of the reaction to start. All right, if a waterfall is a spontaneous process, from waterfall we understand that water goes from high to low. And water goes from high to low is a spontaneous process. So the water from low to high becomes non-spontaneous process because it's opposite direction. And we understand water will not go from a low position to high. Of course, unless we put some effort to it. For example, like a pump. Okay. You can see the fountain, okay, everywhere. Okay, in Florida, especially in a pond or lagoon. So down underneath, everybody knows there's a pump. So we keep putting energy into the water so that we can shoot water to the higher place, so it can form a beautiful fountain, or in our garden, having a waterfall. So let me speak a slightly different way. For a non-spontaneous process to occur, the system must be supplied with a continuous input of energy externally. Two keywords I want you guys to understand. First, the energy input must come from externally, not from the system. From where? Surroundings. And the continuous, this word means if we stop that input, this process stops. Kind of like if we unplug the power, we will no longer have a fountain. Because, like I said, water does not go from a lower position to the high one. That is not spontaneous, which is we call non-spontaneous process. Two concepts I want you guys to learn and learn how to differentiate. One is called spontaneous process, which is we just have just discussed. The other one is called instantaneous process. Instantaneous process, the word instantaneous comes from chapter 14 when we discuss instantaneous rate, if you still remember. Initial rate is an instantaneous rate. So instantaneous means it happens right away. It is a kinetic term, not thermodynamic term. Spontaneous is a thermodynamic term. It's not the kinetic term. I'm trying to make a loop right here, sounds like. But I just want to point out, spontaneous reaction, it may not occurred right away. So for example, it takes years for the iron to rust in certain occasions. Like that big piece of iron work, and it takes years to get rusted. But for the same reaction, if we make that iron particle so small, it can burn right away when it is exposed to the air. So same reaction, it can be instantaneous, sudden busted, or occurs right away, or not. So I just want you guys to understand, for the spontaneous process, it does not necessarily mean it's going to go right away. Or it doesn't go very fast. Sometimes it can go years, or sometimes billion years. Remember, we have an extra credit work in chapter 14 for the diamond, right? So we figure out it took eons to have a diamond converted to the graphite. So that's the difference. Okay, we understand that graphite turning into, diamond turning into graphite is a spontaneous process. It will happen. For how long? We don't care. Or from the point of thermodynamics, we don't care. Only we care about how fast it is belong to kinetics. Okay, I just want you guys to understand the difference between these two different processes, spontaneous versus instantaneous. All right, our goal, or first goal in this chapter, is to predict a spontaneous process. Based on the law that we have learned from chapter 5, let's see whether it can help us to understand when we predict the spontaneous process. Remember, the first law that we have learned from chapter 5 is the first law of thermodynamics. Can this law predict the spontaneous process? We understand the first law of thermodynamics is energy of a universe is constant. In other words, delta E of the universe is equal to 0. So that is why we understand the energy of the system and energy change of the surroundings. They are equal in value, but have a different sign. All right, so we have established a relationship between the system and surroundings in terms of energy or energy flow. But what about this delta E? Delta E actually is turned out equals to Q plus W. The problem is neither Q nor W is a state function. They both non-state function. Depends on the pathway system chooses. That is a troublesome tool for us to consider, because when we have the reaction, okay, we understand the reaction is going to take place. For example, burning gasoline and oxygen. We understand the reaction is going to take place. But we cannot use either Q or W to tell us how this reaction is spontaneous, because the Q could be negative, the Q could be positive, the W could be 0, W could be positive, negative. So because both of these functions depends on the path the system chooses. So that is the reason why we cannot use this first law of thermodynamics to help us understand in order for us to predict the spontaneous process. All right, what about sign of delta H? the heat of the reaction. Remember, H is the enthalpy, and the delta H is the heat of the reaction. If delta H of the reaction is negative, everybody understand here, it's an exothermic reaction. Would that be a spontaneous process? As we look at this example, the rusting of iron, of course it is a spontaneous process. It's going to happen no matter how, right? It could be very fast or it could be very slow, take years to finish. And when we look at the delta H of the reaction, it's negative, a lot negative. We are talking about 1.6 megajoules for such a reaction. For per mole of this reaction, of course. So when we look at this, we understand the reaction releases a lot of heat by carrying out the reaction, and we understand make it stable, right? So from non-stable to stable, that should be spontaneous. That makes sense. So this is a spontaneous process. But the question is, would every exothermic reaction spontaneous? Let's look at this one. This is not a chemical reaction. It is just condensation reaction, right? From gas to the liquid. So that we try to condense water into the liquid. Okay, so when we look at this delta H of the reaction, of physical change, it's negative. Is that spontaneous? Most of you probably going to say yes. Yes, in normal condition. But what happens if we have the temperature that's greater than 100? Remember, water boils at 100 degrees. If our temperature that's above 100 degrees, will any liquid exist? Of course not. Since this reaction does not exist, right? There's no condensation ever occurred above 100 degrees. You understand that it's not a spontaneous process. At the temperature that's higher than 100 degrees. So we find out, yes, to a certain extent, right? So when we look at the sign of the delta H and the magnitude of delta H of a reaction, we can certainly understand whether that is going to be a spontaneous process or not. And of course, we can check with the endothermic reaction, because endothermic reaction means the reaction requires heat, right? So if heat stops, as we discussed from chapter 5, heat should be considered as the reactant. So if one of the reactant is out as the heat stops, the reaction stops. Sounds like a non-spontaneous process for me, or to me. Now we can use an example of splitting of water to understand this better. This reaction without heat won't happen, because that's as much amount of heat that the equation requires a lot of heat, and more than a half of a megajoules. Will that happen? Of course not. Because if you think it's a spontaneous process, there wouldn't be any more water left in this world. Because after a billion years, water would be gone then. So now we understand this reaction is not going to take place. Will all the endothermic reaction be non-spontaneous process? Let's look at dissolution and dissociation of sodium chloride. The heat of the reaction is positive, meaning, according to that positive delta H, it could be a non-spontaneous process. Would that be non-spontaneous process? Of course it's not. Because if we throw the small pitch of sodium chloride into the water, it will disappear. This dissolution and dissociation process of sodium chloride actually is spontaneous. Again, we wound up the same conclusion. Yes, to a certain extent. In other words, they're under the condition. What condition? You may realize temperature. So from this analysis of different type of chemical reactions, we realize yes, delta H definitely a good parameter for us to determine the spontaneity, which is spontaneous, right? Spontaneity of the process, but it's not accurate enough. Because not all the exothermic reaction is spontaneous, not all the endothermic reaction are non-spontaneous. So we understand there gotta be more factors that are involved when we predict the spontaneous process. We understand temperature could be one. Now, what we have to ask ourselves is if there are more. In order for us to realize there is a more factor involved in order to predict the spontaneity of the process, I'd like to use a certain example to make a point about the freedom of motion of the particles, because that is a very important concept so that we can draw another important thermodynamic variable in this chapter. Let's look at the evaporation of water. When we look at the value here, remember evaporization is the reverse reaction of condensation. If condensation has a negative sign for the reaction, as a heat of a reaction, evaporization must have a plus sign. So, sounds like a non-spontaneous process to me, but if you put a glass of water on a table in your kitchen, on the bench of your kitchen, give it a few days, like 4 or 5 days, you will find out water has been evaporated because the water left in the glass is not the same amount of glass we put in a few days ago. What does that mean? That means this process actually is spontaneous. How do we understand this spontaneous process? Okay, we start with the water, and we understand water is a liquid, and from what we understand about the liquid, they're close packed, they can move around a little bit, but not much. But once they become gas, those gas molecule has far more freedom to move around, right? So that the freedom of motion becomes one of the key for us to understand the driving force for a non-spontaneous process from the numbers, of course, to become spontaneous. Of course, the freedom of motion usually results disorder. Just imagine if I have 2 kids that are quiet, they're quiet order, right? So not much of motion around. If you got the 2 hyperactive kids in a house, man, think about to control those kids, you're gonna have a headache because everything becomes disorder. So the more freedom of motion indicates the greater the disorder. All right, so now we understand that we can use disorder to describe as a driving force to have a reaction turns in the spontaneous. Will that be the only source? Let's look at another endothermic reaction, the dissociation of a sodium chloride. As we already discussed, dissociation of sodium chloride is a spontaneous process because once we put sodium chloride into the water, it disappears. And also we know for sure by carrying out the chemical reactions, we proved the existence of chloride, because if we add sodium nitrate in the solution, and we have silver chloride. So that means sodium chloride has fallen apart so that it can give us a sodium and a chloride, in which chloride will react with silver later on to form silver chloride. All right, so imagine that we got a piece of sodium chloride right here and surrounded by the water molecules. And we have water molecules that have certain motion because it's a liquid, right? What about sodium chloride? Do they have all the particles of the cations and anions? Do they have any motion? No, they don't. Because they are restrained in their position and they cannot move around. So that's why you can see we have some water molecules that moves. We have some ions that cannot move. It's quite clear. Move, not move. Then what happens if we have sodium chloride dissolving in the water? Sodium chloride and water, they all move. That means we have reached the dispersion of the energy. Okay. Sodium chloride gains energy and becomes more energetic. So we dissipated the energy from move, not move, to the all move. That is another driving force. Because when sodium and chloride start moving around in solution, they reach the random and disorder. And of course, that makes the problem a lot more complicated then. Because once we have sodium that's pure, water is pure, mixed together, we call ourselves a mixture. We increase complexity to the system. So the 4 words that help us to understand the driving force to make a reaction spontaneous. If we can make the reaction more disordered, more random, more energy dissipated or dispersion, and make the system more complicated. All of these will be the driving force to make process spontaneous. All right, now we need a measure. We need a certain variable to describe all these 4 words. Therefore, we introduce entropy. Entropy is a measure of the randomness of the system. And entropy, by the symbol, we realize it is a state function. State function meaning it depends on initial and final state, and it is independent of the pathway system chooses. So for example, evaporation of water to the gas, and I can have this water in the freezer, let it freeze into the solid ice, and then put it back in the temperature, in the room temperature, make it a liquid again, and let it evaporate. Will that make any difference in entropy? Of course it's not. Because all we need is these 2 states. It has nothing to do with whether we have to make the water to the ice, then ice to back out water. So from this understanding, entropy must be the state function. And of course, we can apply delta, which is a change, to the entropy. So say we change the entropy must equal to the entropy at the final state minus the entropy at the initial state. If delta S greater than 0, meaning there's going to be more motion, more random. If delta S is less than 0, we'll talk about the process that leads less random than less motion. All right, now we have entropy that is introduced to describe the randomness dispersion of the energy, dispersion of the energy, complexity, and disorder of the system. But I want you to keep in mind that thermodynamics is a science. Science means we must have a mathematical model to support it, to prove it. Just what kind of a mathematical tool can we use to describe this concept of entropy? The popular way to do this is the microstate. Since it's so popular, people wouldn't think of any other way. The definition of a microstate is the ways to achieve random arrangement. So now let's see how this microstate and entropy can relate together. From an entropy point of view, we understand the ordered arrangement of particles is not going to be favored because it's a less random, less motion. It could be less motion, resulting the less value of entropy. Right? Delta S is equal to 0. So that is not going to be favored for spontaneity of the reaction, as of now we understand. And of course, the more random arrangement of particles become more probable, and entropy as a result will increase. Now we find out we can use the random arrangement to represent the entropy. And from the second statement in green, we realize in order to have a more random arrangement, the value of a microstate must be bigger or in the larger value. So now we're going to conduct one of the most famous experiments in mind, because this experiment cannot be done in reality. That means particles in the flasks. So let's think about an imaginary reaction or the experiment. So we got the two flasks, okay, and they connected by the valve, and both flasks are absolutely vacuum to begin with, and then we put one particle in one of the flasks, or maybe 2 and 3. By having particles on one side, only one flask, there's only one arrangement, because there could be any more, right? One particle in a flask, that's it. Or 3 particles all together in a flask. But let's imagine what happens if we relieve the valve. If we have one particle that's on the left of the flask after the valve is open, right? And we have possibility for the particle moving to another flask. That means we have 2 arrangements for particle to stay. Okay, so 2 arrangement sounds like a 2 with the first power. What about the 2 particles? 2 particles, as we lay out, we find out that there could be 4 arrangements, as shown in the picture. 4 equals to 2 with the second power. So it seems like the exponent indicates the number of particles. Let's try it out with the 3 particles. And of course, our observation is confirmed. With the 3 particles, we wound up with 8 possibilities or the arrangement for those particles to stay. So people might wonder what happens if there's 3 flasks. Sure, we can do that too. So that would be 3 the first, 3 the second, 3 the third. But would that be an important argument for us to change the wave So the microstate to something like 3 powered by the number of particles instead of 2. Well, in mathematics or in physics, there's not much of a difference. Why there isn't much of a difference? Because all we want to do is to make a point. 2 with the power of n or 3 with the power of n, they all show the exactly same mathematical train. That is good enough for physics. So that is why it's easier for us to understand with the 2 flasks instead of 3. So W equals to 2 raised by the power of n is good enough as a representation for the microstate. And I would like to remind you that W can increase exponentially as we increase the value of exponent. So for example, 2 to the 10th power, that is roughly equal to 1,000, 1,024 to be exact. So that is why in computer science, when we say 1K, that is 2 powered by the 10th power, 2 to the 10th. What about a mega, a million? That would be 1,000 times 1,000 in terms of exponents, 2 to the 20th power. A billion, 2 to the 30th power. So the value of W increases exponentially as we increase the value of n. Let's imagine if we have a flask with 1 mole of gas particles. And imagine what would happen if we open up the valve. Let the gas particle go to the other flask. That definitely will give us the macro state that equals to 2 with the power of Avogadro number. That is a number that's way beyond our imagination. Remember, if n equals to 30, W is already in the scale of 1 billion. And just imagine if exponent is equal to 6.022 times 10 to the 23rd, that value of W, I don't think any computer or calculator in this world can get us this value. Alright, so once we understand that part, here's the problem. How can we use macrostate to represent entropy? Some people, very smart, okay, 2 people actually, so here I'm going to mention one. He's co-founder of KMT theory, as we mentioned in chapter 10 in the gas chapter. His name is Ludwig Boltzmann. He said, don't worry about it. Let's take the log of this macrostate. Then we can manage this number. So he proposed a famous equation. Entropy equals to some constant times the log of macrostate. That constant turned later to be a Boltzmann constant. We named that constant after him. And it turned out as universal gas constant divided by the Avogadro number. It is a shame that he died in 1906, because if he could live a little bit longer, he would have got Nobel Prize in physics, because that is one of the most beautiful equations in physics. He explained, this equation explains some very complicated process with a very beautiful, simple, splendid mathematical equation. In 2011, I had a conference in Vienna, Austria, and being a chemist, I know all about this, so that's why I paid a visit to his tomb, Boltzmann's tomb. I want you guys to look at what has been inscribed into his tombstone. S equals to K times log of W. That is enough said about his contribution in science. Okay. So we do not have a lot of beautiful, simple mathematical equation that can explain some profound phenomenon in physics. E equals to mc squared is 1, so that is why make Einstein a household name. And S equals to K times log of W is another. That is just some information for you to know. So once we understand the entropy and how the entropy can be represented by mathematics, so we now see that entropy is a function of a microstate. So now people start to get thinking, can entropy used to describe or to determine the spontaneous process? Remember, for all we have said, if we find out more randomness, more diversity, and more energy dispersed, and more complex, they become driving force for chemical reaction. But that is not the whole picture. In order for us to predict the spontaneity of the process, it's not just a system, it is the universe. So if we want to have a spontaneous process, the entropy change of the universe must be greater than 0. It means the entropy change of the system is only part of it. We also have to consider the entropy change of the surroundings. You need to take that into account. And we also have to make sure that when we add up these two delta S's together, it must be a positive value because it's greater than 0. So sometimes we start to see the system becomes more disordered because of the endothermic reaction. And sometimes we find our surrounding becomes more disordered if we burn out in exothermic reaction, right? But nevertheless, for all cases that are spontaneous, the sum of the two must be greater than 0. We cannot just focus on one. We have to consider the both. So with that in mind, I'd like you to think about some philosophical questions about the second law of thermodynamics. Are organisms, for example, us, are the product of second law of thermodynamics? In other words, given time of evolution, okay, let's point out in the science view, not just, I do not want to get this related to something else. So just from a scientific point of view, are we the product of a spontaneous process? When we think about it, look at us. Okay, so we are made of billions of cells. Okay, so those cells are highly organized. Okay, organized is a better word for entropy, right? Because when we say something organized, that means less random. So for highly organized organisms like us, why are we here? Because that is against the second law of thermodynamics. Because thermodynamics tells us it should become more random. I believe this is one of the questions my professor tested me, okay, in my PhD exam. And this is his first question, meaning the easiest question in my PhD exam from that professor. Well, this is what I said. We need to think not just a system. We need to think about the environment around us in terms of thermodynamics, surroundings. Of course, okay, so we are more so the body, so our cells and our body are more organized. But there are also some words I want you guys to pay attention first. Diverse. Okay. Cell, although inside our body, is a very special organized, right? So liver cell, the cell in the liver is very different from the cell in our brain or in our skin. So it's very much diverse. As a result, it's a lot more complicated. So the keywords for entropy here is complexity. Do we have any other keywords that can support for us to answer that question? Yes, we are the product of the second law of thermodynamics. Let's think about our surroundings. The moment we are born, we breathe, right? And every breath in and out, we are making a mess to our surroundings. When we breathe in, okay, so 78% of nitrogen, 21% of oxygen. When we breathe out, we got more compounds in air. Besides nitrogen and oxygen, we introduce carbon dioxide and vapor, water vapor. Once we have those gas molecules all mixed, that contributes a lot in the increase of entropy to our surroundings. Because the mixing gas particles, as we soon will learn, will contribute a lot or increase a lot in terms of entropy. And of course, we are a warm-blooded animal, a living being, and we irradiate to our surroundings with infrared. So some molecules in the air actually can absorb this infrared radiation to get heated, get excited, and get more energy, and move faster, cause more randomness. And not even mention the mess we made as the society. So all of which adding up, that will set off this positive entropy that we have, so say, as a living being. So delta S of the system plus delta S of surroundings, it can be positive, greater than 0. So we are not in a contradictory with the second law of thermodynamics. We are the product of the second law of thermodynamics. Of course, that's all in science. So, in order for us to recognize something being spontaneous, we must think about not just a system, we need to think about the surroundings as well. Because only the delta S of these two adding together being positive before we can call it spontaneous. Now that we understand the second law of thermodynamics, okay, and we also understand we can use entropy to describe the spontaneity of the process. And of course, we understand that entropy again is the measure of randomness, right? Complexity, so on and so forth. Now, let's do another imaginary experiment. So say the temperature has dropped down all the way to 0 degree Kelvin. We cannot go negative in temperature according to the scale for Kelvin, right? So the lowest temperature is 0 degree. Once we have temperature at 0 degree, everything freezes in solid. even though it's helium or hydrogen, they become solid as well. What is even more or even worse is when we add a 0 degree, any particle, including atoms and molecules, has no motion whatsoever. Of course, that includes electron. That means at 0 degree, there will be no atom because the electron collides with the nucleus. Atoms no longer exist. There will be no substance or anything else. So that is the reason why we cannot have or obtain 0 degree Kelvin. We can approach it, but we can never attain the 0 degrees Kelvin. Well, at 0 degree, any particle has no motion whatsoever. That leaves the only way to arrange particles. Just have one particle next to another. Because they cannot move anymore. So they converge to the certain point and form a particle, forming a solid. So there's only one way. Put one to another, next to another. That definitely makes us excited. Because if there's only one way to arrange particles, what is the macro state then? 1. According to the Boltzmann equation, S equals to K times log of W. Log of 1, 0. So entropy of everything at 0 degree Kelvin is 0. That's a bombshell. Because it tells us the entropy of a perfectly ordered crystalline substance at 0 degrees Kelvin. At 0 degree Kelvin is 0. S equals to 0. That means S, entropy, has absolute value. So as a consequence, we can measure both the difference in entropy between the two states, or simply we measure absolute value of entropy for either state. Entropy is different from enthalpy or energy, because energy and enthalpy, they do not have absolute value. When we try to use them, we need to put the delta H in front of it. But for entropy, we do have absolute value. So that's the reason why if you check the end of the textbook, so there's a thermodynamic value or the parameters, okay, delta H, delta G, and you see there's not delta S, that's an S for pure substances. That is the conclusion we can draw from the third law of thermodynamics. All right, now we have 0th law, 4th law, 2nd law, and the 3rd law of thermodynamics. These 4 laws gives us the thermodynamics. There are a few cases that we can use our common knowledge and our understanding of entropy to predict whether the entropy is going to increase or decrease. One of the most important case is changing temperature. Let's imagine if you have gas particles that's in a room or in a box. At a low temperature, for example, just a temperature a little bit higher than the boiling point, so that the gas particles does not have a lot of energy. They become gas but not flying very fast. So they are low in temperature, they are less motion, and remember, they are just a little bit higher than the boiling point. So the average speed of these particles is very small, and as a result, as we can see at the lower temperature, the average speed is small, and also you see this. Okay, you see this distribution or dispersion of the energy is much narrower. In other words, those particles are not that active. They do not have much of energy at a lower temperature. But once we have a higher temperature, according to that equation, as the temperature increases, speed increases as well. Of course, at a high temperature, particle moves faster. If a particle moves faster, as you can see, not only we see the greater speed, we also see much wider of the energy distribution. Or in other words, we start to see much wider dispersion of energy of the molecule. Remember, dispersion or disperse is a key word for entropy. Right? And more energetic of the particle, more random it becomes. Just like you've got too many kids active, hyperactive in the room, and it doesn't take long to make a whole lot of mess in the house, right? So that is why people usually put random with the words like chaos. Okay? So more chaotic the system is, the greater the entropy it is. So from this discussion, and we understand as temperature increases, entropy increases. And that is the fundamental conclusion we can draw from this case. And this is the conclusion or the statement we can use to explain some other cases when we try to predict the entropy of the system. Our second case is a change in the physical state. When we talk about a change of physical state, we realize that we got a solid, not have too much of a motion, does not have a lot of kinetic energy. We understand we have a gas that has a lot of kinetic energy, liquid is somewhere in between. But if we look at the boiling point, the freezing point of water, we realize water, okay, so ice must have the lowest temperature in order to be stable. Gas must have a temperature greater than 100 to become stable. According to what we have discussed, remember, the higher the temperature, the more the entropy. So that certainly explains why solid has less entropy than the liquid, and the liquid has less entropy than the gas. And that is true for all substances. No exception. So the entropy increases with the rising temperature actually explains why we have that rank. Okay? The order of entropies among the solid, liquid, and gas. And also in generally, the change in the physical states are more important than any other changes. How can we understand that statement? We need to look at this picture. And I want you guys to notice that when we have a solid to the liquid, this is a jump of entropy. We call it entropy of fusion. And this is entropy of what we call vaporization. You can tell how big the jump it is. Since the jump is much bigger, very much bigger from liquid to the gas, so the entropy of gas is much, much greater than the liquid and greater than the solid as well. And because of this big jump, if we find out something that's in a gas, no matter how simple, how whatever, the entropy of gas is greater than that of a solid or the liquid. So that is the reason why, because of the much bigger jump between the solid, liquid and solid, we can come up with a conclusion that the change in the physical state, especially gas, are more important than any other changes. The third case I'd like to discuss is related to our experiment in chemistry, dissolution and or dissociation. So let's talk about dissolve something in the liquid. If we dissolve a liquid in the liquid, the entropy of the solution is pretty much the two entropies combined. That means there's no net entropy increase. The reason for that is if you look at ethanol, okay, if we zoom up, we find out there are some intermolecular forces that hold ethanol molecules together as a liquid. You understand that's going to be double force because ethanol is a polar molecule. You understand there's going to be dispersion forces that existed in all covalent molecules. And for ethanol, there's hydrogen bond. Is there any difference we see in the water? No. Three forces exist in the water. Once we mix these two together, we still have these three forces. There's nothing new. So that is the reason why we do not see the big jump in entropy of the solution when we mix these two liquids together. When we dissolve the solid into the liquid, we start to see the entropy solution is greater than the two combined. Why? Think about this. The difference of the entropy of solid and the difference of the entropy of the liquid. Remember, when we dissolve the solid, so the molecule of the solid will stay in what state? Liquid. So the solid, quote, in liquid, unquote, must have a greater entropy than a solid, as we already discussed in the previous slide. Entropy of a liquid is greater than the entropy of the solid. So if you want to use this equation in purple to explain, so entropy is roughly the same if you have two liquids combined. Now you have a solid. Solid has a less entropy. Remember, solid has less entropy. So for example, 8 equals to 4 plus 4. If we have 8 and 3 and 4, because solid has less entropy, so 8 is definitely greater than 3 plus 4. So now we realize entropy of solution is greater than the two entropies combined. The solid plus the entropy of the solvent. And once we understand that dissolve the solid into the liquid can have this entropy increase, so that also works true with ionic compound. So say if we have sodium chloride, that's true. But I just want you guys to understand that statement only works for the metal with the +1 charge. Because once the metal has more than +1 charge, things are going to change. The reason is with the more charge accumulated on the metal, the water that's surrounding becomes more arranged. That definitely decreases the entropy. But in that course, as far as we're concerned in this Chem 2 class, it's easily safe to say by dissolve and dissociating the ionic solid, entropy of solution increases as a result, because I'm not going to give you any ionic compound whose cation has other than +1 charge. So that is for sure. So you can think safe to use this statement. Well, as we try to dissolve the gas in a different media, let me erase this. Since it's going to be slightly different, if we want to dissolve the gas into the liquid, the entropy, as a matter of fact, decreases. And it decreases a lot. Same reason. Remember, the solution is roughly equal to the entropy of a liquid plus the entropy of a solvent. Now, we replace the entropy of the liquid with the entropy of a gas. Let me use the simple number to explain. So 8 equals to 4 plus 4. Remember, the entropy of gas is greater. So 8, 16, and 4. Of course, the sign is going to change. So 8 is less than 16 plus 4. So that certainly explains that a solution with a gas inside, that definitely hurts the entropy. So that is the reason why, remember when we have a soda, when we open up the lid, gas coming out. That is a spontaneous process because gas wants to be out so that entropy can be greater. The delta S should be positive. And then because delta S is positive, gas escapes from the solution. If we have two gases mix each other, entropy will be much greater than these two entropies combined. Of course, the proof of this should be discussed in a much higher level chemistry class. So I just want you guys to recognize this conclusion. The fourth case, we're talking about chemical reactions that involve in gas. So here I'd like to use dinitrogen tetroxide and nitrogen dioxide as an example. If we have a 5 and 2 O4 molecules, remember after reaction we could have a 10 NO2s because of stoichiometry. So this is a four-order reaction. We'll generate more gas molecules. Guess what? The delta S is going to be increasing. Why increasing? Because we got more gas molecules. Gas molecules leads more randomly because they're flying around and cannot be traced, or not that can be. It's not going to be that easy. So definitely make more disorder to the reaction or in the system. The entropy must be greater than 0 for this process. From this analysis and discussion, so now we realize if we have a gas reaction with the delta N gas, right, delta N greater than 0, entropy increases as a result. If you have a reverse reaction, say if you have a gas reaction with the delta N gas less than 0, less gas particles as a product, delta S of the reaction is less than 0. So if the reaction performs gases or produces more gases, this is what the reaction favors. The fifth scenario we'd like to talk about here is about atomic size and the molecular complexity. It states entropy increases as atomic or ionic size increases. That certainly makes sense because as we increase the sizes, there will be more room for electron to reach randomness. Right? So that is the reason why the entropy increases within the group from top down. And also works for the ions. So where the sodium fluoride has the least entropy, where the sodium iodide has the greatest, because iodide has a much greater size than the fluoride. Size is greater, more room for electrons of the iodide to become randomness. Entropy also increases as the molecular complexity increases. In order for us to understand this picture, this statement, I gave you a couple pictures for you guys to think about. NO, nitrogen monoxide. when we talk about the motion, especially the motion of the atoms with a bond, within a bond, so between the nitrogen and the oxygen in that nitrogen monoxide, the only motion we can think about is a stretching, going back and forth, back and forth. But if we talk about nitrogen dioxide, besides the stretching, we have more different ways of movement of the bond. Right? So we got two stretchings going on, and also we got a band going on, left and right. So as we increase the complexity of the molecules, we find out that we got more and more ways of movement of the bonding atoms. And of course, if we have N2O4, and we have additional movement as well. We got stretching of the fifth bond. And also we have those motions that's not aligned in the plane anymore. Remember, N2O4 is a planar molecule. Also, we can have a motion that is not within the plane. So as we increase the complexity of the molecules, definitely we introduce more type of movement for the bond within the molecule. That definitely increases the entropy, because complexity is a word for the entropy. From all these 5 cases, I just want you guys to understand that the change of entropy due to the changes in the physical state usually trumps to the rest. So that means changes in the entropy of the change of state is usually much larger than the change due to the increase of molecular complexity. And we usually consider molecular complexity as a last resource to consider for predicting the entropy. So when we summarize all these cases, I combine the first and 2 all together because we understand, okay, the state, the entropy change due to state actually is direct conclusion of the entropy change with temperature. So entropy increases with the rising temperature. That is most fundamental, and we can use this to explain the change in the state. And also we have discussed the dissolution and dissociation. Okay, so we explain why it's a greater sign or roughly equal sign or less sign for entropy of solution and solid and solvent combined. And of course, we use the entropy of liquid, or entropy of gas to explain how the sign works. In our case, the third case, okay, we talk about gas. Remember, gas possesses the most entropy. So if we have a gas produced by the reaction, definitely that's going to be the driving force for the reaction, because that's the increase in entropy. Of course, the last one, complexity of the molecule or the size of an atom or the molecule, will be the last one for us to consider. In this way, we have set up the priority. So when we try to predict the entropy, we follow the cases. First, has the highest priority, see if there's a temperature change or a change in the state. Second, whether we needed to see whether there's going to be a dissolution problem going on. Third, if there is a gas forming by the chemical reaction. If all the 3 above is out, we consider the 4th scenario. All right, so let's try to understand predicting entropy a little bit better with these 6 questions in our example. And I'd like to remind you that first 5 questions are under the constant temperature, the same temperature. All right, so our first question, 1 mole of sulfur dioxide and 1 mole of sulfur trioxide. And when we look at this question, we realize they both have the same moles. They both have the same type of atoms, sulfur and oxygen, and they both have the same state. All right, and of course they are the same temperature. Since they are in the same temperature and same state, case 1 is out. Scenario 1 is out. And what about the solution? Doesn't happen. What about more gas? Doesn't happen. Same moles. So that leaves us only the fourth scenario, complexity of a molecule. Sulfur trioxide, more complex. So 1 mole of sulfur trioxide has a higher entropy. In our second question, we have 1 mole of carbon dioxide in solid and 1 mole of carbon dioxide in gas. The one in the gas, of course, definitely has higher entropy. There's no doubt. So third question, 3 moles of oxygen versus 2 moles of ozone, O3. That's interesting because when we look at this question, they all have the same number of oxygen atoms, right? 6 oxygen atoms, 6 oxygen atoms. As we look at this, we realize they have the same temperature, same state, so first scenario is out. Second scenario, dissolution, dissociation, not happening. Third, although this has a reaction with more gas, yes, we do have difference in moles of gases. Right? We got 3 moles of O2 and 2 moles of O3. Which one has a higher entropy then? 3 moles of O2. Because there are more gas particles. That's as simple as this. More gas particles, more randomness, more dispersion in energy, the greater the entropy it is. 1 mole of potassium bromide versus 1 mole of potassium bromide in aqueous. The one in aqueous definitely has a higher entropy, there's no doubt. 1 mole of CF4 in liquid versus 1 mole of CL4 in liquid. Again, same temperature, same state. Scenario 1 is out. Scenario 2, the solution not happening because we talk about a pure substance. Third, number of moles not happening because we have a 1 mole in both of substance. That leaves out the scenario 4. Which one is larger? Which one is more complex? CCl4, carbon tetrachloride. So 1 mole of CCl4 has a higher entropy. As a last question, seawater in the mid-winter at 0 degree or in the mid-summer at 32 degrees Celsius. Of course, the one with the higher temperature definitely has a greater entropy. So I just hope with this 6 exercises, we understand how to predict the entropy in these various scenarios. Now we're going to talk about the standard molar entropy. The definition here is the entropy of 1 mole of a pure substance at standard state condition. So what is the standard state condition? So I'd like to jog your memory a little bit. So that state includes the most stable form of substance in the physical state in which it exists in the room temperature at 1 atm. Of course, there must be pure substance for solid or the liquid. If we talk about solution, that is going to be 1 molar, and for gas, that's going to be 1 atm. Why do we need a standard molar entropy? Because we can compare those substance or the process with equal amount of material when we predict the relative value of entropy for different substances in transformation. For example, 1 mole of sulfur in solid versus 1 mole of sulfur in liquid. Or better yet, to the chemical reaction. So we can start with 1 mole of something so that we can compare the rest. The unit for standard molar entropy is joule per mole per Kelvin. That's interesting because it shares the same unit as universal gas constant. I just want to remind you, okay, this is an interesting point because later on we are going to use this unit to derive some important equations. So once we have a standard molar entropy, then we can develop an even more important concept called standard entropy of the reaction, delta S0 of the reaction. That is a case of Hess's law. For example, if you have more generic reaction like AA plus BB, something yields CC plus DD, and according to Hess's law, the delta S of the zero of the reaction, zero, remember, means standard state, is equal to C, the coefficient of C, times the entropy, standard molar entropy of the C, plus D times standard molar entropy of D, and on until we exhaust all the product, then minus the coefficient of A times the standard molar entropy of A plus the B, coefficient B times standard molar entropy of B, on. And I just want you guys to realize the one on the front actually comes from the product. The second term is the reactant. So that is Hess's law. The only thing that we need to change is we switch H with S. And I would like to remind you, the M and N, the coefficients of product and reactant, now has a unit in moles. And the moles multiplied by joules per mole, which is the unit of S0. The delta S0 of a reaction is joule per Kelvin, not the joules per mole per Kelvin anymore. I just want you guys to realize the fine difference between the delta S0 and S0. Unlike the delta HF0 and the delta GF0, the one that we're going to talk about later, delta S0 for element in a stable form is no longer zero. Why? Because of the third law of thermodynamics. When we have standard state, the temperature is not a 0K. It's a 0 degrees Celsius. No, I'm sorry, 25 degrees Celsius, which is a 298 Kelvin. That's quite a temperature, good enough the temperature for those particles to gain randomness and to gain speed to reach randomness. Therefore, we do not see zero as S0 for anything. Again, one thing that we need to recognize is the application of Hess's law on entropy. The last slide of this section of the lecture is to go through our example problems to understand a little bit more about how we're going to use the Hess's law to calculate the standard entropy change of the reaction. This kind of a reaction is quite obvious because we are given standard entropy of everything. And then we're going to calculate delta S0 of the reaction. First thing first, we need to make sure that we have reaction balanced. Without a balancing reaction, we're going to get the wrong coefficients. Once we get the wrong coefficient, we are not going to get a calculation right. And by the way, balancing chemical reaction is chemistry. If you got it wrong, anything later on based on this wrong balanced chemical equation makes no sense for getting any credit. So it is very important for us to balance the equation first, or at least to check the equation provided to make sure it is balanced. Once we have this equation balanced, so we can apply the Hess's law on the entropy. So we can write, remember, product minus reactant. So we got 1 here, so that's why it's 1 mole. We got 1 moles of water, so that's 1 moles of water. And we add their entropies all together, minus the sum of entropies from the reactants. Remember, that's 2, so that's why we have 2. So we have 2 here, so that's 2. And we got 1 mole of carbon monoxide, dioxide, so that's 1 mole of carbon dioxide. The calculation leads us negative 134 kilojoules per mole. For secondary reaction, again, make sure that we have this equation balanced, because that makes a whole difference. As we plug those numbers in, remember, we start with the product, so that's 1 here. We got 1 mole. 3 moles of hydrogen, 3 moles of hydrogen, minus 2 moles of iron, 2 moles of iron, 3 moles of water, 3 moles of water. We calculate and get the answer negative 142.2 joules per Kelvin. That is it for this section of the lecture. So in this lecture, we discussed the spontaneous process. In order for us to predict the spontaneous process, we introduced the concept called entropy. Entropy is equally important as enthalpy in thermodynamics. So we must understand what entropy is, what entropy is representing, and what is the math that support the entropy, which is a macro state. And also 2 additional laws that's based on the entropy. Second law of thermodynamics to tell us how we judge the spontaneous process. The third law tells us what is the absolute value for an entropy of the substance. And also later on, we learn that since entropy is a state function, we can use Hess's law to calculate the entropy change of the reaction. That is it for this section of the lecture. I'll see you guys in the second half of this lecture of chapter 18. Thank you.